Describe 3 conditions for when a function does not have a derivative. So in this video, we're going to be talking about the conditions for when a function does not have a derivative. So let's remember that the derivative represents the slope of a tangent line. So that means if a tangent line exists, or if a tangent line can actually be drawn through a particular point, then the function has a derivative at that point. Woo! However, if a tangent line doesn't exist, meaning we cannot draw a tangent line, then that function doesn't have a derivative at that point. So to figure out when a function does not have a derivative, basically the question we have to answer is when do tangent lines not exist? So if we can find or we can figure out conditions for when tangent lines do not exist, we can figure out when a function will not have a derivative. So let's take a look at that first condition. Our first condition is that a function is not continuous. So if a function is not continuous at a point, then the function is not differentiable at a point. So again, if a function is not continuous, it's not differentiable, meaning if it's not continuous, we can't draw a tangent line. So let's take a look. So we can see here we have a jump discontinuity at x equals -4. So looking at this value right here. Now if we were to draw a tangent line through the point at x equals -4, if we draw a tangent line as we approach from the left-hand side, we would get a tangent line that looks something like that. So again, this is the tangent line as x approaches -4 from the left. Well, if we then approach -4 from the right, we can see that we are going to get a completely different tangent line. So how can we have 2 tangent lines? And how can we have 2 different tangent lines that are so far apart on this particular function? And the answer is we can't. So therefore, if a function is not continuous, it's not differentiable. If we move to our next discontinuity here at x equals 2, a similar situation, we can see that we'd have a tangent line that would look something like so, as x approaches 2 from the left, and then something like so, as x approaches 2 from the right. So again, not continuous, no derivative. Well then let's take a look at x equals 4, because now this is a hole in the graph. So now if we want to draw a tangent line through x equals -4, well, we have a problem because there's no point at x equals -4. There's a hole. So if we tried to draw a hole, we would just, completely fall through the graph. Ah! So again, not continuous means not differentiable. And then the last type of discontinuity here is the infinite discontinuity. The reason if an infinite discontinuity fails is covered in another condition. So we'll come back to that in just a moment. But again, if a function is not continuous, it means we can't draw a tangent line, which means it's not differentiable. So condition 2, a derivative is not going to exist if we have an abrupt change in the slope. So when the slope changes abruptly, the graph has what we call a corner or a cusp. So for example, our absolute value graph, the slope changes abruptly. It goes from being -1 to +1. And when this particular event happens, this is going to form a corner because it's a nice point. If we have this weird piecewise function there where one piece is linear and the other piece looks to be some quadratic or a polynomial, this particular abrupt change is known as a cusp. And again, both of these are where the slope changes abruptly. So if a function has a corner or a cusp at a point, then the function does not have a derivative at that point because we can't draw a tangent line. And similarly with the discontinuity, we run into the same issue here. If we were to draw a tangent line on our absolute value graph as x approaches 0 from the left, we would have a tangent line that goes like this. And if we would draw a tangent line as x approaches 0 from the right, we would have a tangent line that looks like this. And we can see that those are two completely different tangent lines with two completely different slopes, so no derivative. And same thing with a cusp. So, I mean, just for make this a little bit easier, let's call this point 3. So, if we found the tangent line as x approaches 3 from the right, we would have a tangent line with a positive slope. And if we were to look at the tangent line as x approaches 3 from the right, we would have a negative slope. Again, an abrupt change. At one single moment, it goes from being positive to being negative. Optimistic to pessimistic. So, no derivative because no agreeable tangent line. And finally, condition number 3. We do not have a derivative when we have a vertical curve or a vertical tangent line. So why does this whole vertical matter? Well, let's think way back to algebra, and let's remember that a vertical tangent line has an undefined slope. I like to think of it, I'm not Spider-Man, I can't climb up a wall, so therefore I can't climb up a vertical tangent line. So, undefined slope. Well, if the vertical line has an undefined slope, that means that we can't have a derivative there because we can't draw a tangent line. So, undefined slope means derivative is undefined, which means there is no derivative at that particular point. So let's take a look. So here we have a cube root function. And if I look here, like if I am this little dude, and I'm hiking up, I'm hiking along, yada-da-da-da-da, oh boy, it's getting a little steep, it's getting a little bit steeper, oh no, and I get to the point right here, and whoop, I slide back down. That's because at this particular point right here, that piece of the graph is going up and down. I can't climb on, I'm not Spider-Man, so I slide right back down. Which means there would be a vertical tangent line at this particular point. And as we know, vertical lines have an undefined slope, so this tangent line doesn't work, therefore no derivative. And if we go back to the graph from the first condition, and we look at the infinite discontinuity at -5, well, we can see that we have a vertical tangent line, aka the asymptote, at 5. So therefore, undefined slope, therefore no tangent line, therefore no derivative. Done. Alright, so let's just take a look at a couple quick examples. In this first example, we just want to identify all the x values where the derivative doesn't exist. So let's go through our 3 conditions. So for condition number 1, we know that a function does not have a derivative when it is not continuous. And we can see here that we have a discontinuity at x equals -1, at x equals 0, and at x equals 1. We also then need to move to step 2, so we're looking for any corners or cusps. And we happen to have this corner right here at x equals 2 because there's an abrupt change. And then finally, we need to check for any vertical tangent lines or vertical pieces of the curve. And if we look at our particular function, as we approach x equals 0 from the left, we can see this particular graph appears to go up forever and ever and ever. So we would have a vertical tangent line at this point. That also happens to be the discontinuity, so we're just, double dipping there. So let's see. A derivative doesn't exist at x equals -1, 0, +1, and 2. Alright, same question, new graph, find all the x values where the derivative doesn't exist. So again, let's go through our conditions. First condition is any spot where a function is not continuous. And we can see that we have a discontinuity at -2 and a discontinuity at 4. Then on to condition 2, do we have any corners or cusps? And we can see here at x equals 0, we're going to have a cusp. So therefore, no derivative at x equals 0. And it doesn't appear as though we have any vertical tangent lines, one could make the argument that at x equals 4, it does appear as though we would have a vertical part of the function right here. My argument would be, well, we don't have enough information about this function. The graph doesn't show us enough to say for sure that's a vertical piece. So I'm not going to include it, but again, the argument could be made that it is. All right, so let's answer the question. A derivative doesn't exist at x equals -2, 0, and +2. All right, and then our final example. We are given these 4 graphs, and we're asked which of the following functions is differentiable at x equals 0. So we need to pick one of these graphs and figure out which one is differentiable at x equals 0. So let's start off with letter A. So we're looking at letter A, and we can see that at x equals 0, we have a corner. So therefore, answer choice A, we're out, not differentiable at 0. If we move on to answer choice B, let's see, at x equals 0, is it continuous? And yes, it is continuous, so it passes condition 1. Is there a corner or cusp at x equals 0? The answer is nope. Is there a vertical tangent line or vertical curve? The answer is no. So therefore, B does appear to have a derivative at x equals 0. Now we'll just move on to identify why C and D are not the answers. Because if we look at C, we have a discontinuity, so fails condition 1. And then if we look at D, at x equals 0, there appears to be a vertical section of this curve, which means no tangent line, which means no derivative. All right, folks, that is it. That is describing 3 conditions for when a function does not have a derivative.